In this video, we're going to look at formal definition of a limit of a sequence. So here we have an is equal to f of n. We have this sequence, and we say this sequence converges to L if the terms of an can be made arbitrarily close to L by choosing n large enough. More precisely, the limit n goes to infinity of an is equal to L, or an approaches L when n goes to infinity, provided that for every epsilon larger than 0, there exists an integer n such that when n is bigger than capital N, the difference between the sequence term, which is an, and its converging limit is less than epsilon. So the idea is that if we can make that difference arbitrarily small, which is basically making epsilon approach 0, then an has to approach L. The limit of an will be L, the limit of the sequence will be L, the sequence converges to L. So let's remove the absolute value. We have absolute value of an minus L is less than epsilon. Now we rewrite this as an minus L is less than epsilon, larger than minus epsilon. And we add L to both sides, and we get an is between L plus epsilon and L minus epsilon. Now, if we draw this on a, let's draw this on a line, you can see that here is the terms of the sequence, which is an. So let's say an is here. Here is L plus epsilon, and here is L minus epsilon. Now, you can tell as epsilon approaches 0, if we pick enough terms, we can make epsilon very, very small. You can see how L plus epsilon approaches L. So we get a limiting value. And that's what we mean by the limit of the sequence being L. So as epsilon approaches 0, an approaches L. That's the basic idea. All right, so here we have a diagram. We can visualize it here. So we have n bigger than n. This implies that an is between L plus epsilon, this is the upper band, and larger than L minus epsilon, this is the lower band. Look at all of these points. You can see that when n is bigger than capital N, all the points are in this band between L minus epsilon and L plus epsilon. So that means as n goes to infinity, the limit of the sequence will approach L. There it is. All right, alternatively, we say that the limit as n goes to infinity of an is equal to infinity if for each positive number m, there is an integer n such that if n is bigger than n, an is bigger than capital N. Let's show that from a diagram. It will be easier to visualize. So here we have when n is bigger than capital N, this implies that an is bigger than capital N. Take a look at these points. You can see how all of them are bigger than capital M as n is bigger than n. And so that means the limit as n goes to infinity of an is equal to infinity. The terms are increasing to infinity. The sequence an diverges to infinity. So that's what it means for a sequence to diverge to infinity. You can see as soon as n is bigger than n, the terms of the sequence are above the horizontal line y equals m, and they shoot off to infinity. All right, let's look at an example. This will be an example of convergence. So consider f of n is equal to an is equal to n divided by n plus 2. This is an example that we looked at before where we found a limit of the sequence. You may recall we divided by the highest power and we found a limit to be 1. We're going to do the same thing. We're going to get the same result, except we're going to apply formal definition of a limit. Part A of the question asks us, if epsilon is equal to 0.03, find an integer n such that when the difference between an and the converging limit L, when that difference is less than epsilon, when n is bigger than n. So we want to find how many terms do we need such that the value of the term of the sequence and its converging limit is less than 0.03. Part B asks us prove that the limit as n goes to infinity of an is equal to 1 by applying the formal definition of the limit of the sequence. Let me write this in. It got erased. All right. So what we have is for part A, we have limit n goes to infinity of n divided by n plus 2 is equal to 1. And we proved that last time using the just dividing by the highest power. So we want to find an integer n such that the difference between an and 1 is less than epsilon is equal to 0.03 when n is bigger than capital N. All right, so we have an minus 1 is equal to an is n divided by n plus 2 minus 1. And simplifying this, taking common denominator, we get n plus 2 in the denominator, and we get n minus n plus 2, and we simplify this. We will get absolute value of minus 2 divided by n plus 2. And since absolute value makes everything positive, we don't need a negative sign. We write this as 2 divided by n plus 2. And this is less than 0.03. Our goal is to solve for n. Now, since n is bigger or equal to 1, we don't need the absolute value, do we? So we can write this as absolute value of 2 over n plus 2 is equal to 2 divided by n plus 2 without the absolute value. All right, so we have 2 divided by n plus 2 less than 0.03, and we want to solve this inequality for n. Flip both sides, and if you flip both sides, this sign will change. So we have n plus 2, flipping the left-hand side, is larger than 1 divided by 0.03, and cross-multiply, we get n plus 2 times 0.03 is larger than 2. So we get n plus 2 larger than 2 divided by 0.03. Simplifying further, subtracting 2 from both sides, n larger than 2 divided by 0.03 minus 2. And that gives us n larger than 2 over 0.03 minus 2. Let me put this in a calculator. Easier to do it that way. 2 divided by 0.03 equals minus 2. That's 64.66 bar. So round up to the next positive integer. That means n bigger than n is just n equals 65. And capital N is 64. That means when small n is bigger than n, or equivalently 65, bigger than 64, then the difference between an and L, the difference between n over n plus 2, and its converging limit, this difference will be less than epsilon. In this case, we set the epsilon to be 0.03. So essentially, it's saying how many terms do we need to have this level of accuracy, such that difference between the value of the term of the sequence and its converging limit is pretty small. If we want it to be, the difference to be 0.03. So basically, a capital N is equal to 64. We need 64 terms such that the difference is less than 0.03. All right. So part B, for every epsilon larger than 0, we have to find an integer n dependent on epsilon such that the difference between an and the converging limit is less than epsilon when n is bigger than n. So we can prove that the limit as n goes to infinity of an is equal to 1. We want to prove it using a formal definition. We've already proved it in by the easy way, just dividing by the highest power. So what we have is an minus 1 is equal to absolute value n divided by n plus 2 minus 1. Taking common denominator, we get 2 divided by n plus 2. And we don't need the absolute value. We get 2 divided by n plus 2. So what this means is that absolute value of an minus 1 is equal to 2 divided by n plus 2. And this is less than epsilon. Let's solve for n as a function of epsilon. We're going to solve this inequality for n, much like we did in the previous question, except in that case, we had a fixed value for epsilon to be 0.03. Now it's just an arbitrary number, epsilon. So we have 2 divided by n plus 2 is less than epsilon. Flip both sides, we get n plus 2. Let me write this properly. N plus 2 divided by 2 larger than 1 over epsilon. And we get n plus 2 larger than 2 over epsilon. Solving for n, and we get n is bigger than 2 over epsilon minus 2. This means for every epsilon larger than 0, we can find an integer capital N larger or equal to 2 over epsilon minus 2, such that the terms of an is equal to n divided by n plus 2 for n bigger than n lie in the interval 1 minus epsilon and 1 plus epsilon. And since we can find an integer n for all epsilon larger than 0, we say this limit exists, and this limit is equal to 1. So what we have proven is that we've proven that for all epsilon larger than 0, the limit of an equals n over n plus 2 exists, and this limit is equal to 1. We've proven that the absolute value of an minus L is less than epsilon. We can make this arbitrarily small when n is bigger than capital N, or equivalently, when n over n plus 2, the value of the term of the sequence, minus the converging limit, which is 1, is less than epsilon. We can make this arbitrarily small when n is bigger than 2 over epsilon minus 2. So you can tell as epsilon approaches 0, n becomes really large. So it's saying that if we have enough terms, many terms, we can make the epsilon arbitrarily small, and hence the sequence n over n plus 2 approaches 1. It has a converging limit of 1. So now sometimes what you will find here, n over 2 over epsilon minus 2 may not be guaranteed to be an integer. Simply round it up to the next positive integer to find n. So let's check our calculation in part A with epsilon equals 0.03. We have capital N is equal to 2 over epsilon minus 2. So we had epsilon to be fixed at 0.03, 2 over 0.03 minus 2. This gives us 64.66 repeating. And we round up to the next positive integer. So we basically need 65 terms such that the difference between an and its converging limit is less than 0.03. And this matches up our answer we did before because it's really the same steps. So we got n equals 65 here. Let's go back to see how what kind of answer we got there. N equals 65. There it is. And both of those are essentially the same answer. All right, thank you.